Because there were dissimilar metals in Galvani's experiment, one being the scalpel, and the frog's leg itself acted as the electrolyte, Volta postulated that Galvani had inadvertently generated the electricity he observed, and it did not come from the frog's leg at all. Alessandro Volta is credited with inventing the voltaic pile, which is what we commonly know today as a battery. Volta has the honor of having the unit of measurement for electrical potential, the volt, named after him. In the 1820s, André-Marie Ampère was instrumental in the study of magnetism and electromagnetics. His research was foundational in the development of motors and generators. The unit of measurement for electric current, the amp, was named after him. In 1827, German physicist George Ohm gave us the mathematical relationship between voltage, current, and resistance. The mathematical formulae are named after him as Ohm's law. The unit of measurement for electrical resistance also takes his name as the ohm. We will study these equations in detail later. The triangle with the V, I, and R are a memory aid we will use to remember the various forms of the equation relating voltage, current, and resistance. Around 1840, James Prescott Joule gave us Joule's first law, more commonly known in electronics as the power law. The power law relates power in terms of voltage and current. The unit of measure for power is the watt, which is named after the Scottish mathematician James Watt, who did extensive work on improving the steam engine.
Now, the jet setters versus the retros.
Ohm's law.
Here we go.
Power law.
Two teams,
are
one
all
goal, and max
foundational
destruction.
elements in the study for this course.
All right, people. It's about survival in the arena today.
Other notable advancements
That's right,
in
June.
electronics
It's
happened
team
quickly.
deathmatch.
A selected list of
Translation,
achievements
shoot
is
first.
as follows.
Think later.
Alexander Graham Bell invented the first practical telephone in 1876.
Firing thermite!
Thomas Edison
Thermite going out!
patented the phonograph in 1878. In 1880, he developed the first commercially practical electric light, and also patented an electric distribution
Watch
system.
out! Over there!
Heinrich Hertz, in 1888, discovered radio waves. Vladimir developed the picture. Eckhart Macaulay developed the first digital computer. Electronics with the invention of the transistor. Dr. Bell Labs invented the transistor in 1947.
Fire a grenade out! Gas grenade out!
Gerald Pearson invented the solar cell in 1954. Jack Kilby and Robert Noyce of Fairchild Semiconductor invented the integrated circuit in 1958.
Watch out! There!
Pet Hoff and Intel invented the microprocessor in 1960.
Firing thermite!
We have come a long way since
Thermite out!
we need to take a moment to say thank you to these brilliant people and others. It is because of their work that we make fun of things. We stand on the shoulders of giants.
Throwing fire a grenade!
There are some basic theoretical ideas in the
Special
study of
delivery.
electricity. Understanding them helps in our projects, giving us knowledge of those strong, reliable circuits. In this section, we'll look at exactly what electricity is, and then take a look at some basic electric circuits. We'll examine the difference between AC and DC electricity, and study the behavior of electricity in a circuit by exploring the properties of voltage, current, and resistance. Then we'll wrap up the theory section with Ohm's law and the power law.
This might burn!
What is electricity? Electricity is a mysterious entity. It is sometimes difficult to understand exactly what it is. Try and understand. We need to get back to it. That's the atom.
All together, group up!
This is a diagram of a lithium atom. All atoms are made up of neutrons, protons, and electrons. neutral electric charge, protons have a positive electric charge, and electrons have a negative. Normally, an atom has a neutral charge. It has the same amount of electrons and protons. Electrons, however, can be easily moved from or to the electron orbitals of an atom, including electrons, thereby becoming either positively or negatively charged. Electronic circuits and electrons moving electronics concerns itself with direction of components. The electronic components are the playing field, and the electrons are the players. The definition of electricity states, electricity, a form of energy resulting from the existence of charged particles, such as electrons, to the static accumulation of charge. The definition further refers to two types of electricity, static electricity, and second, dynamic, or an electric current. Static electricity is exactly that. It is an electric charge that is not moving. A great example of this is rubbing a balloon on a sweater or your hair and sticking it to a wall. The charges sit on the surfaces of the
Just
object,
30
yet
seconds
don't
left on the
move.
clock.
An imbalance of
Concentration is
electric
key in
charge
research
causes the surfaces to attract or repel. Like charges repel, opposite charges attract. Let's take a look. Here we see a wool sweater, a balloon, and a wall. We see the charges on each object as red positive charges and the negative charges. To begin with, all the surfaces have an equal amount of negative and positive charges. As we move
The
the
Retros
balloon
showed their
on the
experience
sweater,
with a smooth
we
win
can
in
rub off
round
some of the
one.
electrons onto the balloons and have a net positive charge on the sweater and a net negative charge on the balloon. We can now see that the sweater and the balloon are
The
oppositely
Retros
charged, so
turned
they
back the clock
attract.
last round. One more win will seal their legacy.
As we move the balloon towards the wall, we see something interesting. The negative charge on the balloon repels the negative charges away from the location of the balloon. So where the balloon and the wall meet, we have a localized opposite charge, negative on the balloon and positive on the wall, which is why we can stick the balloon to the wall. Opposites attract.
Firing thermite! Stay side by side!
Electric current is what happens when electrons flow through a conductor, such as copper wire. Electrons move from atom to atom, resulting in an electric current. We can see this here in a very simple circuit of a flashlight, consisting of a battery, a filament light bulb, some wire, and a switch. The animation gives a visualization of electron flow or current flow through an electric circuit.
Threat detected! Down there!
Any arrangement of electrical components connected so that there is some form of current. Typically, there is a current or voltage source and a number of components connected with wire and circuit to a conductor. No matter how complex the circuit is, all circuits The basic series circuit consists of a source of electrical energy, a battery or a source,
Watch
a
out!
load,
Guardian turret! There!
some components and other devices, and of course some conductors to connect everything together. For a series circuit, everything is connected in series. In a series circuit, all the current flows through every device. A break anywhere in the circuit interrupts the flow of current. The circuit to the right is a series circuit. It consists of a
Using
battery
pyro grenade!
as the voltage source, two light bulbs as the load, and a switch together with the
Gas
connector
grenade
point.
out!
all the current flows through each and every piece of the circuit. We see that if we open the switch, breaking the circuit, the current flow stops. Closing the switch, completing the circuit, current flow resumes.
Firing thermite! Watch out! Take that! Gather up, team!
Without first having to flow through another component.
Everyone stay side by side.
Here we have a parallel
Enemy!
circuit with multiple light bulbs.
Firing thermite!
To affect the other.
Thermite going out! Careful, up there!
Disable the entire circuit. Bring the circuit at the power source. Completing the circuit,
Everyone, stay
source
together.
resumes current flow to the entire circuit. Many circuits have combination parallel and series. Complicated many paths between the following. In this example, we see the current flow through a complex circuit. The animation gives an idea of different currents through the different circuit elements. Many circuits are very complex. Analyzing them mathematically is complex. However, a large multitude of circuits are of simple complexity. Analysis reduces to identifying the series and parallel sections.
Enemy
Finding the
spotted! Down
analysis
there!
on each section.
Gas grenade out!
Can you spot the series sections and the parallel sections in this circuit? We need to understand that all circuits, no matter how simple or complex, are made up of a combination of series and parallel circuits. Knowing this will help us design our circuits with confidence and skill.
Talking some fire!
Direct current. It means that the current is flowing in one direction only.
Stick together!
DC current is generated by DC sources, such as batteries and solar cells. The battery
In
in
a
your
match
car or
that felt like a
flashlight
throwback
generates DC
masterpiece,
current.
the Retros won
If
this
current
team
flows in two
deathmatch with
directions,
timeless
alternating,
strategy and
we call it
finesse.
AC current, which is short for alternating current. Alternating current is generated by generators or inverters. Normally our house current is of the AC direction. It alternates 60 or 50 cycles per second, depending where in the world we live. Here we have two identical circuits of a flashlight. Identical, except that the left circuit is powered by a DC battery, and the right circuit is powered by an AC source. We can see in the DC circuit current moving only in one direction. In the AC circuit, we see the current moving back and forth. In the DC circuit, from the voltage graph, we see that voltage is constant over time. In the AC circuit, we see that the voltage alternates in the form of a sine wave. This is characteristic of currents produced by generators in a power plant. In this course, we'll be dealing primarily with DC circuits, although we will take a look at some special cases of some special AC circuits. To get a feel for the properties of electricity and its behavior in a circuit, we need to understand in a general sense what the quantities of current, voltage, resistance, and power represent. We can use a water analogy, comparing electron flow through a conductor to water flow through a pipe to help us understand these properties. Current. Electrical current is the flow of electrons through a conductor, just like water flow through a pipe is. We can have small and large currents, depending on how much water flows through the pipe in a given time. Electrical current would be the amount of electrons flowing through a conductor in a given amount of time. Electrical current is measured in amperes, or amps for short. Voltage. Voltage is often referred to as the potential of an electric current. Using the water analogy, it is analogous to the pressure of the water in the pipe. The higher the voltage, the higher the pressure is. Pressure in a pipe depends on the source driving the flow, such as a pump. The same is true for pressure or potential
And
in an
now,
electric
the
circuit.
Retros
The
up
higher the
against
voltage source,
the
the
Overdogs.
greater the pressure or potential.
Let's see who's got the
Electrical
deadliest
potential
aim,
is
folks.
measured in
Here we
volts.
go.
Get ready for a nostalgia bomb,
Resistance
people.
is quite simply
TDM is
that.
back.
Resistance
And with
to
the
current.
firepower these teams are
All
packing, it's going to be
materials
an
resist the flow of
explosive
electrical
showdown.
current to varying degrees depending on their properties. In the water analogy, this equates to restrictions in water flow that are tied to
Everyone
dams,
side by
fittings,
side.
valves, pipe friction, etc. Electrical resistance is ohms. Power. Power is the amount of energy
Teams, stay united.
It is
All
the
right,
product
game
of
on.
current and voltage. We have to think of work as a result of what is done and the energy consumed to produce that work.
Throwing fire.
Water energy.
Tossing a flashbang.
Turn water line, for instance. In an electric circuit, this would equate to how the current and voltage work to drive an electric motor or a light bulb, for instance. Electrical power is measured in watts.
Watch out there.
Here we see our electrical circuit alongside our water energy. The electrical circuit consists of some conductors and a device for work, that is the light bulb. We can see the current flow represented by the electrons flowing through the conductors.
Flashing crap.
In the water analogy, the power source is represented by the pump, the conductors by the pump cylinders, as we increase the current, we see that the current increases and also more work is done. That is, the bulb burns brighter.
Throwing
On
a
the water
flashbang.
analogy side, we see that the height of the water in the tank increases, representing
Let's
the
stick
increase in
together,
pressure.
team. Got a
The water
contestant.
flow
There.
increases in temperature, and the turbine spins faster, showing that more work is done. It's a simple water analogy, a tangible illustration of how the electrical properties of
All
current,
right, let's cause some
voltage,
chaos.
resistance, and power relate to one another. Now that we know what current, voltage, and resistance are, we're ready to look at some math.
Pyro grenade out.
Ohm's law is a simple equation that relates current, voltage, and resistance in terms of triangle V over I and R is a memory aid. Remember the different versions of the equations for Ohm's law. V represents voltage, which is sometimes designated with an equivalent to V. I is for current, and R is for ohm. The units for both current and resistance
Throwing some points.
ohms. Use Ohm's law to solve for one in terms of any of the others. So knowing any two of the three components lets solve for the other. Current is the voltage divided by the resistance. I equals V over R. Voltage is the current times the resistance. V times the voltage. And resistance is voltage divided by the current. R equals V
Special
over R.
delivery. Throwing fire.
Here we have a visual
Using
demonstration of
gas
Ohm's
grenade.
law. We can see the effects in the circuit by varying voltage and resistance. Increasing voltage results in the current in the circuit increasing.
Using a flash.
10 seconds. The retros start sharp, proving they've still got what it takes to win
Increasing
in style.
resistance causes the current in the circuit to decrease.
10 seconds left.
Decreasing voltage results in current decreasing.
The Retros took
wait is
control
over. Here we
last
go.
round. One more, and they'll secure the match.
And decreasing resistance causes the current to increase.
This will burn. Flashbang out. Throwing a flashbang. Poison out.
The mathematical
Now stick
relationship
together.
between power, current, and voltage is known as the power law. Power equals current times voltage. P equals I times V. The unit of measure for power is the watt. This is an extremely useful equation, so remember it, and we'll use it a lot. Combining Ohm's law with the power law allows us to solve the power in
Flashing
terms
crack.
of current and resistance.
Tossing a flashbang.
Here we
Throwing
see
pyro
showing
grenade.
all the possible equations between current, voltage, resistance, and power. the upper left quadrant, you see current defined in terms of
This might
voltage,
burn!
resistance, and power. Finally, in the lower right quadrant, and resistance. Keep this chart close by. It is a handy tool as we design our circuits. So this brings us to the end of our theory section. By now, we have a good understanding of what electricity actually is, and the difference between static electricity and electric current.
Watch out! Over
We
here!
should be able to identify different types of electric circuits: series and parallel, simple and
Danger down
complex.
there!
We should also understand the differences between alternating and direct current and their sources. With the water analogy, we should have a quantitative view of voltage, current, and resistance. The foundation and equations of Ohm's law and power law should now be a part of our knowledge base. These basic foundations are
Together,
equipped us
stay
well
close,
as we
finally.
now move to more practical applications
Down
and circuits.
Down here! Watch out! Over there! Using
In
pyro
this module,
grenade!
we'll take a look at starting to build some simple circuits using breadboards. Breadboards are handy little devices that let us quickly build circuits. Components are easily inserted within a breadboard. Connections quickly made to work up live circuits. The breadboard is allows us to swap components and make changes to our circuits.
Tightening things up!
We can quickly see the practical effects of
Rolling.
changes and make adjustments to get the circuit performance we are looking for.
Everyone, stay
In this
together!
section of the course, we're going to use a virtual breadboard called fritzing.
Flashy,
We'll use
flashy!
fritzing as a teaching tool to show how to get from a schematic drawing of a circuit to an actual breadboard layout. You can download the latest version at
Causing some fire!
www.fritzing.org. Fritzing allows us to create circuit sketches. Here we have opened an untitled sketch. Fritzing creates circuits as schematic and render them into breadboard, or go straight to breadboard. The schematic is created automatically
Clean
alongside.
slate! Let's make it
We'll
count!
start in breadboard. To the right, bring many number parts into one. Let's bring in a small breadboard.
Special delivery! Threat detected! Outgoing gas grenade! Flashbang out! Causing some fire!
When a particular part is selected, you can see in the lower right corner the part properties. Select different configurations of breadboards by changing the properties.
With a blend of classic charm and
Here we
smart
can change
plays,
the
the
breadboard to a
Retros
smaller
emerged
version of the
victorious in this team deathmatch. Congratulations on a stellar performance from the entire team
We
here
can
at
pick
the
different
finals.
configurations of breadboard just by selecting on the properties. We'll start with the half-size breadboard, with our plus and minus buses highlighted. Breadboards come in various sizes, differing in the number of rows and columns they have. Most breadboards have similar configurations. You can use a single breadboard or multiple breadboards to build a circuit, each breadboard dealing with a particular aspect of a circuit. You'll soon get used to building circuits with breadboards and how they help to refine and streamline your designs. The spacing of the contact points is typically 0.1 inches or 2.54 millimeters. This allows for easy insertion of ICs of the same pin spacing. Other components can be inserted easily. With a few jumpers, complete circuits can be built up quickly. It is important to understand how the contact points are connected. The breadboard is separated down the middle with a channel. This is typically where an integrated circuit would straddle, so that all its pins land on isolated columns of contacts. The highlighted pins show areas of common electrical connection. The contacts are arranged in rows and columns. Each column, 1 to 30 for this breadboard, has contacts in rows A through E common and contacts in rows F through J common. Any device inserted into the same column in rows A, B, C, D, or E will be connected, and any device inserted into row F, G, H, I, or J will be connected if on the same column. The rows are not connected.
Okay, the socialites versus the high notes. Blink fast, shoot faster.
Along
This
the
is
top
TDM. Let's
and
go.
along the bottom, we have two buttons.
Get
They are
ready for
marked
pure
blue
adrenaline.
and red,
This is
or
TDM
minus and
at
plus,
its finest.
and are common
Let's
through
see
the
how
whole
these
bus.
contestants handle.
Anything inserted into the red for the plus bus
This way first!
and anything inserted into the blue for the minus bus. These buses are handy to use power supply.
Group up! Group up! Spotted an enemy! There! Knock the gas out!
Before we can build the schematic diagram,
Watch out!
schematic
Guardian
control,
turret! Over
shows
there!
us in symbol form the components of the circuit. Connect them with wires. Let's build a
Using
really
pyro
simple
grenade!
circuit. LED flashlight. We'll select the components
Watch
from the
out!
part
Over
sheet.
there!
First, we'll need an LED.
There! Watch out! Over there! Thanks a million.
Next, we'll need some kind of power source.
Massive advantage for the socialite!
And most importantly, we'll need a current system. The battery is capable of generating more current than a little LED. We have chosen a super bright LED that will be happy with around 20 milliamps of current.
Got the
15
poison! Not the
milliamps.
remedy! Watch out! Over there!
Throw in
This'll burn!
zooming in. And we'll just rearrange the components to make it easier.
Firing thermite! Going fire! Gas grenade
Now we'll
out!
need to connect the components. So let's go to our parts list. Select our wire. And we'll make our components.
Threat detected! Going out! Come on!
SMD, which is surface mount. We'll leave it at PhD, which is through hole.
Thermite out!
Diode,
Watch out! Over here!
5mm through hole.
Over there!
It's just for fun.
Outgoing gas grenade!
And the resistor is the one that we have to select in order to get the proper flow characteristics to the drive. We had already mentioned we're going to use a which is quite functional at 20 milliamps. So using Ohm's
Throwing
law,
fire!
Every
volt
second
average,
counts. No
we
time
would
to
calculate
waste.
the value of the resistance. So calculating we use the familiar Ohm's law.
Threat detected!
Is R equals E over I. that R
Watch out!
equals
Over
9
there!
divided by 0,
Lock the gas in!
which gives us a value for R1 of 400. We only have 470.
10 seconds left.
So that's close enough.
Tossing some fire!
Going back to our schematic there, we'll select R1 as 470.
The high notes delivered a flawless opener, starting strong
There
and
we
in
have it, our
sync.
complete schematic circuit with proper values and component properties. Now switching back to breadboard mode, we can see how the software has placed our components in an actual
Coming
real
off a
view.
brilliant display,
go!
the high notes are ready to
The little
harmonize
dash
their way
line
to victory.
show our circuit connections by what we would call air wires, which show the circuit connection that's running.
Throwing pyro grenade!
So let's start moving our components around the wires of our circuit. Switch.
Firing thermite!
You can see green highlighted areas that show the power buses for each of our terminals. The onboard circuit traces. So now we've made that connection.
Okay, here we go!
Almost connected with a little wire. And that's our circuit. So all the air wires are connected, everything is connected up, and we have a
Here we
fully
go.
functional circuit.
Thermite out!
So now let's save this sketch.
Enemy got me.
We're going to save it, and we are going to call it Rebellion Launcher.
Watch out over there.
Pyro grenade out! Firing thermite!
So that's it.
Thermite out!
A switch, resistor, a power source, and a load, which is our
Using gas
LED.
grenade!
Let's do something a little more exciting. For our light flash circuit, we're going to use the standard 555 timer as the circuit.
Pyro grenade out!
555 timer is what we call a functional electronic. It has a number of discrete components of the signal resulting in a particular function. Strategic selection of a few off-chip components can give functional blocks very powerful uses. The 555 is an extremely useful little
Watch out
device,
there!
and it can offer two modes. One is astable, the other is monostable.
Causing some
The
fire!
wired 555 is an astable
Watch out there!
control the flashing of an LED. The parts that we're going to need for our 555 LED flasher circuit are as follows. We'll need a 555 timer.
Stick side by side!
Since we're using a breadboard, we'll want to
Pyro grenade out!
DIP, which stands for dual input.
Watch out! Over there! Outgoing gas!
16-volt screw grater. A 1K ohm resistor. A 100K ohm resistor. A 470 ohm resistor. All the resistors are important. We're not passing along.
Firing thermite!
So we standard 180
Throwing fire!
Thou hast saved me from the abyss.
Need a 9-volt battery and a battery strap. And of course we'll need an LED.
Special delivery!
Our breadboard and jumper. Now all our components all have leads. We don't want to
Thermite going out!
I've already created a sketch convincing for the 555 timer astable circuit. If you take a look at this, there are a number of things that we can see. Take for instance the battery. You can see that one end is connected to a 9-volt terminal and the other end to a funny looking symbol which is actually the ground potential.
Fire
see that everything that is connected in the circuit, although it's not physically connected as well, it's magnetically and also we have 3 node connections and 2 ground connections. This is a way that we can clean up our schematics without having lines drawing all over the This allows for common connections. Switching to the breadboard now, we can see the components laid out, connected by air wires, ready to be placed in the breadboard. All that stuff to do is put the components onto the breadboard and then make our column traces on the breadboard or with jumpers.
The
We'll do a
socialites even the
combination of both.
score. The final round
We'll do this
promises quite a
time-lapse
performance.
photography here so that you can get a quick overview of how this is done.
The intensity is
Eyes up,
unmatched
stay
as we
sharp.
step into the tie-breaking round.
Danger down there! Throwing fire!
There are lots of ways to make the connections. You'll get the hang of keeping things simple and need with some practice.
Right out! Watch out! Up there!
For our basic astable circuit, the frequency of the oscillations is given by the 1.2 divided by R1 BR2 times C1. We chose these values for our circuit so that the frequency of the flashes is about 1.4 seconds per second. Let's see what happens when we change the value of C1.
Copy some
Let's
fire!
change it to a smaller value by a factor of 10. We'll substitute the 1 frequency. We should see that a flash is much quicker, 10 times quicker according to our equation. On the other hand, if we put a capacitor in place of C1, we should get a very slow oscillation, 10 times slower.
Thermite out!
Here we have an actual circuit operating here with all the components as specified as 10 microfarad capacitor. Let's try and change the 10 microfarad capacitor to the 1 microfarad.
Threat detected! Thermite going out!
You see after swapping it, the LED doesn't. Let's try it.
Poison out!
Expect it to be very slow.
Firing thermite! Throwing pyro grenade! Danger down there!
Try again, the 1 microfarad capacitor.
Team, stay together! Focus! Let's go!
Then back to our design capacitor at 10 microfarads.
This might burn!
Roughly at a flashing rate of 1.4 seconds per second. For those who are interested, T1, or the on time, is given by the equation T1 is equal to 0.693 times R1 plus R2 times C1. T2 is given by the equation T2 is equal to 0.693 times R2 times C1 for a state operation.
Thermite going out!
You can see the values of R1 and R2 the duty cycle. Try it out. See if you can find any applications for this person.
Locked in! Let's go! Enemy! Watch out! There!
Breadboards are extremely useful for prototyping temporary circuits. Build our different demo circuits, which is easy and quick. Breadboards do, however, have their limitations.
Pyro grenade out!
Very complicated.
Using gas
Quite
grenade!
Jumpers can get knocked off if you're not careful. There is some contact resistance on the spring contacts, and this can make a difference in some circuits. High frequency circuits are not breadboards are not usually or hardy circuit solution. Breadboards, on the other hand, can be used in conjunction with other methods, Later on, we'll cover some more complicated and permanent capacitor, LEDs, 5x5 timer. Let's take a closer look at some of the basic building blocks. Combine different fashions to obtain the desired result.
Fireman hack!
Very complex circuits can be broken down into its primary components.
Watch out! Over there!
Components can be categorized
This
into
way
two basic
first.
categories. One is passive, and the other is active. Passive
Thermite out! Thermite out! Spotted an enemy! Over there!
The passive component is not capable of power gain and is
Bringing
not the
elegance
source
and
of energy.
precision, the
In the
socialites
context
outclassed
of
their
electronic
rivals and
technology,
secured
there are
a
stricter
social
guidelines for
victory.
Electronic engineers view this term usually in correlation with circuit analysis, which involves methods of finding the currents through and the voltages across other components in the network. We're going to use a very loose categorization of components, and in fact some of what we are going to consider as passive components could by definition be considered active components. Passive components that we are going to look at include wire and cable, switches, relays, resistors, capacitors, and once we've taken a look at these components, we'll look at a basic resistor capacitor circuit. Wire is by far the most important common component in electrical circuits, so much so that it is taken for granted. It is very important, however, that the right type of wire be selected for each circuit and circuit element. Wire is a conductor, usually copper, and is usually covered by an insulator, most often plastic, rubber, or lacquer. It is either solid or stranded. Stranded wire is more expensive, so it is used in situations where the flexing of wire is likely to occur. A stranded wire has better flexing properties than solid wire. Your test leads for your digital voltmeter, for example, are made of stranded wire. The copper conductors are sometimes tinned, which makes it easier to solder. The current carrying capability of wire is determined by its diameter. Larger diameter wires can carry more current. The diameter of the wire is measured in gauge. Don't get confused here, as a larger gauge number means a smaller diameter. Small gauge is a larger diameter. Using a wire that cannot carry the current in a circuit will get you quickly into trouble. The wire will overheat and the consequences can be catastrophic. Always use conductors large enough to carry the current. A cable is simply a number of conductors bundled together or in a common jacket. Other considerations for wire selection, especially for signal wire, that is, wire carrying data, especially at high frequencies, is the capacitive quality of the wire. This is a function of the conductors and insulators used in the making of the wire or cable. Shielding from noise is also important, and a foil or braided shield is often found in signal wire. Coax, Ethernet cat cables, and audio cables all take these signal properties into consideration. The cables are designed and manufactured specific to the application. Here is a wire gauge that shows the relative sizes for standard wire gauges. Mechanical switches are used to interrupt or permit current flow in a circuit. They can also be used to direct current to different circuit paths, or to select different signals to be used in a circuit. There are countless configurations of switch circuits. They vary from single pole to multi-pole contacts. The action can be push button, toggle, slide, or rotary, and the contacts can be either normally closed or normally open. Let's take a look at a number of them to give you an idea of how versatile they are. Here is a schematic of a simple single pole, single throw switch. We call it single pole because it only controls one circuit path. It is called single throw because we can only select one contact point. We see the contact points on the switch drawn by the circles. The leads from the switch show the circuit connection points, and the switch portion in the middle shows how the contact is made between the two contact points. The short form designation for this switch is SPST, which stands for single pole, single throw. This switch is a single pole double throw configuration. Still, one common connection, thus single pole. However, now we can select or direct to two different paths. The switch is always close to one of the circuit paths, either L1 or L2. The designation for this switch is SPDT, for single pole double throw. Here's a symbol of a more complicated switch. Can you figure out the configuration? We would call this switch a double pole single throw. Double pole because we have two circuit paths
Our contestants are about to clash in the heart of Monaco, where the difference between victory and defeat literally lurks around every corner.
Shows that the switches for each pole are mechanically connected.
The Boundless,
the switches
the
therefore
Powerhouses,
operate together.
The Big Splash, and finally,
what
the
would you
Retros.
say is the configuration of this switch?
It's game time, folks.
It is a double pole double throw. Two circuits.
The tournament's first round begins here, and discipline will be tested.
There's an undeniable surety to how the Retros play. They bring a level of veteran assurance into this tournament that you just can't teach.
They control their contact closures
Watch
by
out!
push
Over
buttons
there!
The
by the
Boundless are
toggle.
strong on Volt 2.
That is, the switch needs to be activated before or
First
released.
elimination is really
And
sending
a
a
spring
message. This match
turns the
is
switch to either normally open or release. Top
Anything
switch
can
is
happen.
a single throw, normally open switch. And the bottom switch is a single throw, normally closed switch.
Watch
As the
out! Over
switch
there!
action is only engaged when it is pressed, so it can be flipped to toggle the switch
We
for
got
every
the
activation
team white.
or pressing
Things
of
are
the switch.
heating up.
Push button
That one
switches
definitely
have
went
multiple
against the
poles
Big
and
Splash.
Thanks a million.
Cash box one!
Other switches include slide switches, rotary switches, switches
Look at that
used
turnover.
Watch out! Over there!
actuators
To the
connected to a
Boundless.
sensing
Firing
device such as a count with a sensor or diaphragm or pressure switch.
Gotcha!
In selecting switches, always observe the switch's maximum voltage and current rating, and stay well below it to make sure the switch is not electrically overloaded.
The Retros are kicking it old school. Cash out started.
While technically not a passive component, electromechanical relays are worth mentioning here because they are a special kind of switch. They have poles and contacts just like the
The
switches we
Powerhouses
have
are back.
But what is different
But
is
the
that the
Boundless
switches
will
are
want to stay
actuated
out
by
of
a
their
small
way.
electromagnetic coil.
Defend on A!
This allows a very
Enemy
small
spotted.
current needed by
There.
the coil to switch larger currents and voltages by means of the
Toxic
switch
gas out.
contacts.
Down there.
The relay is most often an interface device. We can use our small current electronic circuits to switch larger currents real-world devices. Here are some schematic diagrams of some electromechanical relays. Note that the switch portions look exactly like our known switch configurations, only the switches are activated by the coil. When selecting relays, you'll need to consider that the coil voltage is compatible with the electronic circuit, and also that the current and voltage rating and contacts of the switches can be
Enemy got me.
for switching.
Gotta reload.
A cash out station just got robbed
Next
by
to
the
wire,
Powerhouses.
resistors are by
Go
far the
for it.
most
Can
common
change the
component
game.
of electronic circuits. They all perform a crucial function, and that is to
I
limit
guess
the
lightning
current.
does strike more than once another team wipe
We've
for the
already
Big
seen that
Splash.
the unit of resistance
Thermite going out.
The greater the ohm value, the greater the resistance to current, and inversely, the less conductive it is. Resistors come in many shapes and sizes.
Launching some fire!
You can find resistor arrays on a dual inline chip package or single inline packages. The type of construction of a resistor is important too. Resistance is used in various resistances such as 1 ohm, technically 0 ohm resistance, but we can find resistors in 0 ohm packages.
On the other end
secure
of
the
the
first
scale,
cash out
we have
as the other
resistors
teams
that
race
measure
to
in mega
respond.
ohms or millions
What
of
a
ohms.
display of teamwork. All members of the band consistently have each other's backs.
When resistors are manufactured,
Full marks to the
the value
powerhouses. They back to cash out.
A great steal led them straight to that one.
tolerance. That is the value the resistor
Scanning
can
for
vary by
opponents.
from its face value. Common tolerances are 10%, 5%, and 1%. For example, a 100
Scanning
ohm
that area.
resistor with 10%
Reviving.
tolerance could range from 90 to 110 ohms.
Back in play!
This is not usually critical in a circuit, but if it is, choose a tighter tolerance regime. The same 100 ohm resistor with 1% tolerance could range from 99 to 101.
The big splash
One
are opening vault
consequence
4.
of resisting current is that heat is generated. The heat generated can be expressed in watts, so a resistor that has a higher power rating will be required to have a higher watt rating.
I'm back! Much appreciated!
Halftime. The
Higher
tension
power
is rising
resistors
by
Go
the
to
minute.
vault 4!
That's for sure, Scotty.
Some
Keep your eyes glued on this epic battle.
Choose a resistor.
Using pyro grenade!
Another outage for the powerhouses as they get
Most
licked again.
resistors are fixed value. Some resistors whose value changes, or have a variable value. There are adjustable resistors called potentiometers whose value can be changed by turning a dial. There are
That's
also
a
variable
solid run
resistors
from
that
one
change the
contestant.
resistance when
Let's see if
exposed
they
to
can
light
keep it going.
or
Taking damage.
temperature. Resistors are identified by color bands. There are 2 color band systems, a 4-band code and a 5-band. To see what the value of a particular resistor is, count the bands
The
and use the
powerhouses
color
are opening
chart
vault
as you
3.
see here.
The big
For a
splash just
4-band
jump-started a
coded
cash
resistor,
out.
the first 2 bands give the resistor
If the
numerical
retros
value,
want to stay relevant,
which is
they need to pick it
multiplied
up.
by a multiplier in the 3rd band. In this resistor, we can see that the first band is green, which corresponds to the value 5. The next band is blue, which corresponds to the value 6.
The powerhouses swooped up
The
a
3rd
cash
band
box.
is yellow, which
The Boundless
multiplies
pushed
the value
boundaries and
of the
stole a
first
cash
two
out.
bands by
They're
10K
signaling
or
something,
10,000.
Scotty. They're saying game on.
So we have 56
Big
times
energy from the
10,000,
powerhouses as they
which is a
drive the action.
560,000 or 560k ohm resistor. The 4th band gives the tolerance, which for this resistor is a gold band, which corresponds to a tolerance of 5%.
Go for a steal on D!
Similarly, for a 5-band code, the first 3 bands give the value of the resistor.
Firing thermite!
The 4th band is multiplied, and the 5th band, tolerance.
Touch the gas tank!
Orange.
The big splash came
Watch out there!
Team wipe again.
And 7.
This might burn!
Resulting in a value of 200 resistor. The
Thermite
final
out! Down there!
tolerance of 1%.
Group up! Come on, revive
Some of
me!
the following are common schematic symbols. This symbol shows a fixed resistor. This symbol shows a variable,
Enemy
or
down!
what we would also call a potentiometer. Note that it has 3
Steal
leads.
on D! Going in!
The next symbol shows a photoresistor.
No, no, no! This is insane!
Yes, the symbol needs it represents a thermistor, which is a resistor that changes its value with temperature.
Communication skills seem to be on point. Great teamwork.
For this example, we have 3 resistors valued at 220 ohms each.
Look sharp.
The
A
total
vault has just
resistance,
rolled in.
therefore, is 660 ohms. Finding the equivalent resistance for resistors connected in parallel.
Pyro
We're
grenade!
already down to the final minute.
Here we
This
have
match
the same
is
resistance
non-stop.
connected in parallel.
Tick-tock, Scotty. Time for
The
some
equation
last-minute
for the total
heroics.
resistance is 1 over the sum of the inverse
A
of the
bit of virtual
resistances added
catastrophe for
together.
the retros. Team
The
wiped.
equivalent resistance
looked a
of
bit
this circuit
outdated out
is
there.
73.33 ohms.
Turn up the power. The powerhouses have just cashed out.
Let's look at a very practical application of resistors.
A new
Voltage
vault
division
just appeared.
often
Let's see
require
who grabs that
problem-to-solve
cash.
when
Locked
designing
in! Let's
circuits.
go!
With
We need
only
to match
30 seconds
outputs
on the
of one
clock, the
circuit
stakes
to accept
couldn't be
inputs from
higher.
another portion of
One
the circuit.
last push could change everything.
Sometimes we need some voltage references, and resistors can provide the solution. The circuit we are going to analyze is called a voltage divider. We'll take a look at the circuit and then do a demo to illustrate its use. A voltage divider, in its simplest form, consists of two resistors connected in
The
series,
first place finish sees the
one
boundless
end
through to the
connected
next
to ground,
round in style.
and the other
I'd
end
like to mention
connected
the
to a voltmeter.
powerhouses as well. They
You can
made
see
the
this in
cut.
the following circuit diagram. As we can see, it is a very simple circuit, very inexpensive to build, just two resistors connected in series. The equation for calculating the output voltage in terms of the input voltage is V out equals V in times resistance A divided by the total resistance, which in our diagram is resistance A plus our resistance B. Let's solve a real-world problem, matching sensor input levels to A to D process levels. Let's assume we have a hardware platform that accepts 0 to 5 volt signals. But the only sensor we could find to measure our physical quantity produces a 0 to 10 volt signal. We need a means of scaling the signal from 0 to 10 volts to 0 to 5 volts in order to be able to use the sensor. Here is our circuit diagram, again, except V in equals 0 to 10 volts and V out is equal to 0 to 5 volts. Looking at our equation again, V out equals V in times RA over the R total. Since our equation is ratiometric, mathematically it doesn't matter what the exact values of the resistors are, only the ratio of them. So for now, let's arbitrarily choose RA is equal to 1 k ohm. Then solving for RB, it is also equal to 1 k ohm. Let's do a mock-up of a real circuit. Here is our circuit diagram. And here is our actual circuit. We've built it up on a breadboard. Here we have resistor A connected to resistor B, and resistor A is connected to ground at this end, and the other end is connected to V out and one end of resistor B, and the free end of resistor B is connected to 10 volts, which is V in. Let's measure V in, that's 10 volts, and measure V out, and that's 5 volts, which is what we expected. So we've solved the problem with a resistor divider, getting a ratio of 10 volts to 5 volts. 10 volts V in, 5 volts V out. Sensor conditioning is another example of a voltage divider. There are many sensors that vary their resistance with respect to a physical property. Resistive sensors can be found that are sensitive to temperature, light, humidity, touch, location, pressure, vibration, as well as many other properties. The sensor conditioning circuit replaces one of the fixed resistors in a voltage divider circuit with a variable resistor. This converts the characteristic resistance of a sensor to a usable voltage. Let's take a look at temperature measurement, for example. We'll use a thermistor for the variable resistor. For a typical thermistor, the resistance versus temperature curve looks like this. This is the curve for a 10 k ohm resistor, which means the value is 10 k ohms at 25 degrees C. The curve is nonlinear, so in order to interpret this data, we would need to build a table or do some form of curve fitting in our process to relate the thermistor's changing value with temperature. But first, we have to get the changing resistance values into something our process can use, which is changing voltage values. Let's calculate the output voltage of our temperature sensing circuit for temperatures of 20 degrees C, 25 degrees C, and 30 degrees C.
We'll assume that our process can accept a 0 to 5 volt signal,
and we'll select RA equal to 10k ohms. Using our equation, V out equals V in times RA over RA plus RB. The resistance versus temperature in tabular format for this range is as shown. So we find RB at 20 degrees C is equal to 12,260 ohms, RB at 25 degrees C is equal to 10,000 ohms, and RB at 30 degrees C is equal to 8,194 ohms. Substituting, V out equals 5 volts times 10,000 ohms divided by 10,000 ohms plus our thermistor. So for V at 20, it's 5 times 10,000 divided by 10,000 plus 12,260, and so on for V25 and also for V30.
So solving, we get V at 20 degrees C, 2.246 volts, V at 25 degrees C equals 2.5 volts, and V at 30 degrees C equals 2.748 volts. Now this is something we can use in our process. We can measure it with our A to D inputs and linearize through code, tables, or equations, and then move on from there. Let's look at a very practical application of resistors. Voltage division is an often required problem to solve when designing circuits. We need to match outputs of one circuit to accept inputs to another portion of a circuit. Sometimes we need some voltage references, and resistors can provide the solution. The circuit we are going to analyze is called the voltage divider. We will look at the circuit and then do a demo to illustrate its use.
A voltage divider, in its simplest form, consists of two resistors connected in a series, one end connected to ground, and the other end connected to a voltage. We can see this in the following circuit diagram. As we can see, it is a very simple circuit, very inexpensive to build, just two resistors connected in series. The equation for calculating the output voltage in terms of the input voltage is V out equals V in times resistance A divided by the total resistance, which in our diagram is resistance A plus our resistance B. Let's solve a real-world problem, matching sensor input levels to A to D process levels. Let's assume we have a hardware platform that accepts 0 to 5 volt signals. But the only sensor we could find to measure our physical quantity produces a 0 to 10 volt signal. We need a means of scaling the signal from 0 to 10 volts to 0 to 5 volts in order to be able to use the sensor. Here is our circuit diagram, again, except V in equals 0 to 10 volts and V out is equal to 0 to 5 volts. Looking at our equation again, V out equals V in times RA over the R total. Since our equation is ratiometric, mathematically it doesn't matter what the exact values of the resistors are, only the ratio of them. So for now, let's arbitrarily choose RA is equal to 1k ohm. Then solving for RB, it is also equal to 1k ohm. Let's do a mock-up of a real circuit. Here's our circuit diagram. And here is our actual circuit. We've built it up on a breadboard. Here we have resistor A connected to resistor B, and resistor A is connected to ground at this end, and the other end is connected to V out and one end of resistor B, and the free end of resistor B is connected to 10 volts, which is V in. Let's measure V in, that's 10 volts, and measure V out, and that's 5 volts, which is what we expected. So we've solved the problem with a resistor divider, getting a ratio of 10 volts to 5 volts. 10 volts V in, 5 volts V out. Sensor conditioning is another example of a voltage divider. There are many sensors that vary their resistance with respect to a physical property. Resistive sensors can be found that are sensitive to temperature, light, humidity, touch, location, pressure, vibration, as well as many other properties. The sensor conditioning circuit replaces one of the fixed resistors in a voltage divider circuit with a variable resistor. This converts the characteristic resistance of a sensor to a usable voltage. Let's take a look at temperature measurement, for example. We'll use a thermistor for the variable resistor. For a typical thermistor, the resistance versus temperature curve looks like this. This is the curve for a 10K ohm resistor, which means the value is 10K ohms at 25 degrees C. The curve is nonlinear, so in order to interpret this data, we would need to build a table or do some form of curve fitting in our process to relate the thermistor's changing value with temperature. But first, we have to get the changing resistance values into something our process can use, which is changing voltage values. Let's calculate the output voltage of our temperature sensing circuit for temperatures of 20 degrees C, 25 degrees C, and 30 degrees C. We'll assume that our process can accept a 0 to 5 volt signal, and we'll select RA equal to 10K ohms. Using our equation, V out equals Vn times RA over RA plus RB. The resistance versus temperature in tabular format for this range is as shown. So we find RB at 20 degrees C is equal to 12,260 ohms, RB at 25 degrees C is equal to 10,000 ohms, and RB at 30 degrees C is equal to 8,194 ohms. Substituting, V out equals 5 volts times 10,000 ohms divided by 10,000 ohms plus R thermistor. So for V at 20, it's 5 times 10,000 divided by 10,000 plus 12,260, and so on for V25 and also for V30. So solving, we get V at 20 degrees C, 2.246 volts, V at 25 degrees C equals 2.5 volts, and V at 30 degrees C equals 2.748 volts. Now this is something we can use in our process. We can measure it with our A to D inputs and linearize through code, tables, or equations, and then move on from there.
Capacitors come in many shapes and sizes and configurations, but they all do the same thing. They store an electrical charge. Let's take a quick look at a capacitor model.
In this model, we see a capacitor made of two conducting plates separated by a dielectric. The plates are connected, one of them to the positive side of a battery and the other to a negative side of the battery. If we increase the voltage on the battery, we can see what happens to the charges on each of the plate. The positive side has a positive charge, and the negative side has a negative charge. Disconnecting the battery, we see that the charge remains. Changing the polarity from one side to the other, we see here the negative charge is now on this plate and the positive charge is on that plate. And the capacitor stores the charge that is placed on it by the battery. The capacitance of the capacitor is determined by a number of things. One is the plate area, the other is the separation between the plates, and the other is the dielectric in between the two plates. We can vary the capacitance by changing the separation in the plate area or the dielectric. Let's increase the separation and see what happens. Capacitance goes down with increased separation. Let's increase the plate area and see what happens. Capacitance goes up with larger plate area. And changing the dielectric also changes the capacitance.
The measurement of capacitance is the farad. Just like resistors, capacitors can have very small capacitance values and go to very big ones. A 1 farad capacitor would be very big, and capacitors are usually orders of magnitude smaller in electronic circuits. Capacitors are often classified by what their dielectric is. Common materials are ceramic, mylar, paper, or even air. The dielectric is selected by the application of the electronic circuit. Different dielectrics have different costs. A ceramic capacitor is quite inexpensive when compared to a mylar capacitor. In digital circuits, the ceramic capacitor may be adequate, but in audio circuits, we would opt for the more expensive mylar capacitor because of noise concerns. In a power supply circuit, we may choose a tantalum or an electrolytic can capacitor because these capacitors can be made in large capacitance values required for power supply circuits. Proper selection of capacitors is an art in of itself. A circuit may work okay with one type of capacitor, but it may work great with another type. Even so, the value is the same. Just as resistors have to be selected with adequate power ratings for the application, so must a capacitor be selected with adequate voltage rating. You need to be aware of the maximum voltage that the capacitor may see in the circuit and select a capacitor that is rated above this voltage and with an ample safety factor. Selecting a capacitor with too low a voltage rating will destroy it, and sometimes with great fanfare, which can be dangerous. Capacitors can have fixed or variable values. We can find variable capacitors such as trim capacitors that can be adjusted with a screwdriver. Older vacuum tube radios have large tuning capacitors with air as the dielectric. These were tuned to tune the frequency of the receiver. And some transducers will change capacitance proportional to the measured element. Many pressure transducers and touchscreens are capacitive devices. Condenser microphones are essentially a capacitor. Condenser is another word for capacitor. We already know that the unit of measurement for capacitance is the farad, but most capacitors are an order of magnitude smaller than a farad. A microfarad is 1/1,000,000th of a farad. It has the prefix of the Greek letter mu. A picofarad is 1/1,000,000th of a farad. It has the prefix of the lowercase p. There are many symbols to show a capacitor in a schematic. Some of the more common ones are fixed, nonpolar, fixed, polar. This means that you must install this capacitor with the plus sign to the positive side of the circuit, and variable or adjustable. The equations for total capacitance are somewhat different for capacitors than for resistors. For a series circuit, we just can't simply add the capacitances. The total capacitance is calculated by taking the inverse of the sum of the inverses of the capacitors in series. For this circuit, we have 3 capacitors of 2.2 microfarads each. Calculating, we have a total capacitance of 0.733 microfarads. Capacitors in parallel are, however, simply added up to get their total capacitance. The total capacitance of this circuit is 6.6 microfarads. Let's build a simple resistor capacitor circuit and illustrate how a capacitor charges and discharges. In this circuit diagram, we have a capacitor hooked up in a couple of different ways. One is a charging circuit and one is a discharging circuit. For the charging circuit, which is the lower loop, we have the capacitor hooked up to a 10 ohm resistor, through a switch, through a 9-volt battery, and then with a return leg back to the other side of the capacitor. The discharging circuit, which is the upper loop, eliminates the battery and is connected to a 10 ohm resistor and a switch, and that to the other side of the capacitor. If we close the switch on the lower loop, on the bottom loop, the charging loop, we'll be able to see on the voltmeter how the capacitor charges. Let's give that a try. We see the voltage rising, the final value, which would be the same as the 9-volt battery. If we remove the battery from the circuit, we see as before, the capacitor holds the charge, remains at 9 volts. If we close the other switch, we'll be able to discharge the capacitor. Same value resistor, no battery, but we're discharging through the 10 ohm resistor. And we see a very typical discharge curve and back down to 0 volts. The RC time constant in RC circuits is very important. It is the time in seconds that it takes for a capacitor to charge to 63.3% of its final charge.